Today let me discuss two problems on CFL. So it's about constructing some CFL given some language. So the first problem that I want to address is this one. So this is just an example taken from that How Profitable Man book. The proof is given but not formally written, kind of semi-formally textual form. So but I want to do it in detail here. So the problem is this one. So this is the language. Okay. So first of all, we are using some notation here. So I'm taking string over this alphabet. This star should not be here. So this star. Okay. So we take string over this alphabet, AB star. And this mod subscript A means the number of A's in this string. So this consists of some A's and B's, right? So for example, here if I take just this string, it contains 2 A's, so that means this thing is 2. Similarly for B, it's the number of B's here, so here it's 1. So if I take empty string, then both this mod A, mod B are 0. Okay. So now the problem is you consider all the strings where the number of A's is equal to the number of B's. Okay. So it's not immediately clear whether this language is a CFL or not, but here we have given a grammar, so that shows that this is a CFL and this is a grammar for that. So now formally we need to prove that this grammar actually generates this language. Okay. So that means we need to prove this, that we can derive some string from the start symbol S here, if and only if the number of A's is equal to the number of B's. So this is what we are supposed to prove in order to prove this. Now when we were constructing DFA, I said that so it's not only about the final state, right? So you have to figure out what the intermediate states are, and we said that it's better to think of some meaning about those intermediate states, right? So what sort of strings correspond to those states? So similarly in the grammar also, the language corresponds to all the strings that you can derive from S, but you also need to think about the other variables that you are using. So it's you have to in your mind think of this set of strings. So what sort of property do they have? So what does this A mean? So now the property I want to impose here is this, that you can derive some string from A if and only if the string has exactly one more A than the B's. Okay, so this is the number of B's. So the number of A is exactly one more than this, and B means it has exactly one less A than B. So that means it has exactly one more B than A. Okay. So this is how I thought of this production, and you should also, when you are constructing something, some grammar for some given language, you should in your mind somehow figure out what this other variables mean. Okay, some sort of meaning. Now you see, I'll use obviously induction to prove that this is true, induction on the length of W. But it is beneficial to prove this stronger statement. Why is this stronger? Because it's saying that this is true and this is true and this is true. Okay, so this entire thing is a single statement. So it has this thing and this thing and this thing. Okay, and we will prove this thing in total using induction on the length of string. So just to be clear, the induction hypothesis, we will assume that all these three statements are true for, say, some length of w or shorter length. Okay, then from that hypothesis we will prove that all of these three hold for longer string. Okay, so just I want to emphasize the point that this is our, so you start from a hypothesis, and when you are proving, it's not just okay that you prove this part and you say that okay, now I have proved this thing. So the proof doesn't hold, because in induction, if this is your induction hypothesis, you have to again prove all of this thing for a longer string, right? Assuming this for a shorter string. So the basis is, so you see that it's coming from AB star. Okay, so not star, AB plus, so that means it has length at least 1. So the basis is starts with length 1, so that means it's just a symbol, it's either A or B, right? So this is true because you see that this S doesn't derive A, sorry, this should be B. So this S doesn't derive A or it doesn't derive B. Why? Because you look at the production, so it's either AB and BA, and you see that A and B, they also generate at least one symbol, or this symbol and then something else. So all the strings that are generated from this A or B, so they itself are of length more than 0. So that means whatever you have here, so it's of length at least 2, right? So that means this does not derive this thing, this does not derive this thing, so this statement is true, right? Because yeah. And similarly here, the only possibility is I mean, it just derives A and it does not derive B. So all the strings that it's deriving, it follows this property. Similarly here, all the string of length 1, it's deriving follows this property. Here all the string of length 1 means just this B, right? So this is the basis. We have proved all these three things for length 1. So now using this as our hypothesis for as I said, shorter string, we need to prove again all these three things for the longer strings. And I broke down the proof. So this is a if and only if, right? So even in here we have sort of two statements, that this implies this and this implies this. So I broke it down into 3 parts, and in each part again we have this 2 direction. So let's just attack this thing first. Okay. So we will prove that if you can derive something from S, then it has equal number of A's and B's. And as I said before, only proving this doesn't complete the proof, right? So because you have to prove all 3, though it looks like this is sufficient for this, but it's not. So okay. Now if you can derive this thing, okay, so what will be the first step in this derivation? So the direct derivation thing here. So what will be the first step? So this should correspond to a production of S, right? So S production. And what sort of S production do we have? Either S goes to AB or it goes to BA. So either the first step is this or the first step is this. Now if it is the case, then this B will eventually generate some string over terminals. So this whole thing is our W, right? Where this X is generated from B. Now since X is shorter than W, so by our induction hypothesis, so this implies now that the number of A here is exactly 1 less than number of B in X, right? So here do we what do we have? So in X we had 1 less A, and here we have this A. So together it means that for this W the number of A's is equal to the number of B's. Similarly here it's just the same thing. So this means that now this A will generate some X. So yeah, this is true. And X is shorter than W. So again, by induction hypothesis, here the number of B's is exactly 1 less than the number of A's. So yeah, this is true. So that means if I take this together, so then the number of A's and B's are equal. So this part, these are trivial. So I should mention that the non-trivial bits are here. So this is symmetric. So if we do one thing, then another is done. So this production, so this this A going to this BAA, and similarly for the similar thing for B. So this is the most clever part of this thing. So now let's attack this thing. So this is done. So let's attack the second component. So no, this is not done. We have only proved this one direction, right? This to this. So we have to prove the other direction. So yeah, the other direction is if the number of A's and B's are equal, so then this implies this thing. So again, it's the same thing, just argued in the opposite direction. So this W, it should either start with A or it should start with B. And since we have covered the basis was for length 1, so that means now we can assume that our W is of length at least 2, right? So yeah, so that means here it starts with A or B, and the remaining X, this is also of length at least 1, because as I said, W is of length at least 2 here. So and since in this W the number of A's and B's are equal, so that means in X the number of A is 1 less than this number of B's. And by induction hypothesis, since this is if and only if, since X is shorter than W, so I can apply induction hypothesis on X, and this means that this X is actually can be derived from this B, right? So that means I have a derivation S going to AB according to this, and then I can do this because I have proved this, and I can derive W. So that means I can derive W from S in this case, and this part is just the mirror thing of that. Just A is replaced, and we are considering B here. So that means in this remaining X part, the number of A is exactly 1 more than B. X is shorter. So again, by induction hypothesis, I apply this, that if this is true, then this is true. So that means it's derived from A, so I have this whole derivation. So S goes to dA and that goes to X and W. Okay, so this thing is done. So as I was saying, the interesting part is here and here, but any one is fine. So another is just similar to that. So let's now just go to this A production. Okay, so now we again break this up into two directions. This if and only if, we first prove that this thing implies this thing, and then next we will prove that this thing implies that thing. So now if you can derive this thing again, the first step of the derivation should be this single step derivation, which corresponds to a production here, right? And as I said, we have already covered the basis here for length 1. So now we can assume that we are dealing with W with length more than 1. So this holds for our induction step. And if this is the case, then you see that we are not using this production. It's just deriving A. So we are not using this. We are either using this or we are using this. So these are two cases, that either the first step is this or the first step is this. And then it derives some AX, where this X is derived from this S, right? And since X is shorter than W, by induction hypothesis we use this. So it says that the number of A is equal to number of B in X. So together if I take this, then for this W, the number of A is exactly 1 more than the number of B. Okay, again it's fine. Now look at this thing. Okay. So what does this say? So we are trying to impose this meaning, right, that it has exactly 1 more A than B's. So now if it starts with B, okay, so in the remaining part we should have exactly 2 more A's than B's, right? So this is something which has this property that it has exactly 1 more A than B. And you are saying that the first symbol is B, so that means in the remaining part you have even 1 less B, so that means the number of A's is 2 more than the number of B's, and that we broke into this 2 part, A and A, right? And here we will use something. So anyway, this direction is fine, but the other direction will we will need some formal some proper argument to justify this thing, this A. But in this direction it works out quite trivially. So that means if this is the case, then this from this A you derive some x1, from this A you derive some x2, and that is your W. So yeah, this x1 is derived from A, and also this x2 is derived from A, right? And both are shorter than W. So by using induction hypothesis again, we know that this has exactly 1 more A than this, than the number of B's. Again, this is true. So if I take the concatenation of this thing, so if I take just this x1, x2, this part alone, so this has exactly 2 more A's than B's. So if I now consider this B also, that means together it has exactly 1 more A than B. So this is again true. Okay. So this direction is done. Now about the reverse direction. Again, this case is kind of trivial. So yeah. So now we are trying to prove this. that this implies this, so in this direction. So like in the S case, we consider two cases, so whether it begins with A or whether it begins with B. And as I said, this length of W is more than 1, so that means this length of X is at least 1. Okay, so it is at least 1, and by this property we know that X contains equal number of A's and B's. So by induction, that means this X should be derivable from S. So I have a derivation here. So I'll first use this production, and then from this S I can derive this X. So I can derive this whole AX, which is W, from A. So this direction is fine if I have this A as a first symbol. So now consider that the first symbol is B. Okay. So that means in the remaining part, as I was saying, in the remaining part we should have this. Okay. So the number of A's is now 2 more than the number of B's in this remaining part, that is X, right? Because only then, if you consider B, so you will have this thing, that number of A's 1 more than number of B's. Now if you have this thing, so then this is the most important part of the whole proof, I think, this one line, and I'll have to explain it in further detail. So this tells you that if you have this, then there must exist a prefix of x1 such that in that prefix the number of A is exactly 1 more than the number of B's. Okay, so you have a string, some A1, A2 up to whatever you are considering the symbol, some AT, whatever. So this is your string where the number of A's is 2 more than the number of B's. So this is saying that so that means there exists some prefix, you can cut it at some place such that the number of A's is exactly 1 more than the number of B's, right? So if that is the case, so this is a prefix of this X. So if this part is, say, X1, and here you have this X2, and together this whole thing is, say, X. Okay, so here if you have exactly 1 more A, and together if you have exactly 2 more A, then even in the remaining part you should have just 1 more A here. So that means here also the number of A is exactly 1 more than this thing. Okay. So and X is concatenation of this thing. So now since this is smaller than this, so individually these two are smaller than this, right? So X1 is smaller than W, X2 is smaller than W. So that means by our induction hypothesis and by this and this, we have that both of these should be derivable from A, right? So that means I can write, I can use this production first. A goes to B, AA, and this A then goes to X1, this A goes to X2, and then this goes to W. Okay. Now, just to elaborate on this part, see, you consider a string, any string, say W, and as I said, it consists of some symbols, A1, A2, and these symbols are, again, so I'm just considering this alphabet consisting of A and B. So it goes up to some point, say it has some length. So the length is n. So length is n, say. So it goes up to n, a_n, right? And if I consider up to ai, the prefix of length ai, so wi is a prefix of w, such that length of wi is I. So that means wi consists of only the first I symbols. So this part is wi. Okay. So now just define this function. So this is an integer between 0 and n. Okay. So and you just notice that this is a trivial thing, that this is a prefix of length 0, so this must be epsilon. This is a prefix of length n, so this must be the whole thing, because n is the, okay, I have it here. So but anyway, you define this function, which is the difference between the number of a's and b's. Okay. So number of a's minus the number of b's for this, for up to this first I symbols. Okay. So that means this domain of this thing is this 0 up to n. Okay. For all this I, 0 up to n, I have this fi, which is this thing. So it starts with 0, right? Because okay, so yeah, so yeah, it starts with 0, because what is f0? That means I'm considering number of a's in w0 and again number of v's in w0. But what is w0? It's just empty string, right? So again, I'm instead of just digging into the symbols and this thing, what did it mean? So it's just the number of the difference of number of a's and b's in the first I symbol. So here I'm considering just 0 many symbols, so everything is 0. 0 minus 0 is 0. And now the next thing you should notice is that this function changes value by 1. So if you go from I to I plus 1, the value changes by either plus 1 or minus 1. It's not that you are at value 3 and you suddenly jump to 5 or you suddenly jump to 0 or something like that. And why is it so? Because you have some difference for this wi. Okay, and if the next symbol is a, so this is considering one more symbol. So if the next symbol is a, so then this part goes up by 1, and if the next symbol is b, then this part goes up by 1. So this thing, either it increases by 1 or it decreases by 1, right? So this holds. So that means if you are considering all the values of this say ft for all the t's in here in this range, okay, and if you have say calculated it for some I and calculated it for some j, and since it changes only by 1, okay, it cannot suddenly jump from here to some low value. So it either goes down by 1 or it either goes up by 1. So since this is the property, okay, so that means if I have this fi here and fj here, so if I take any intermediate integer, so if I take any c which is between these two things, not okay, not wi, so I should have written fi and fj. Okay. So if I choose any c between this fi and fj, right, so that means this thing have to pass through this c value, right? So starting from here, it is reaching here, so at some point in its journey it must cross the c, and cross means it has to pass through. It is not the case that at this, say suppose the c is 3 and here you have 5 and in the next step you have 2 without going through 3. So it's not the case because it is changing only by 1, right? So yeah, so that means if you will have some k between this I and j, such that this f of k is your chosen c. Okay, so this is the case. So if you choose any c between this fi and fj, so that means there exists a k between I and j such that this fk is c. So so that means in here what I was arguing, here the difference in this number of a's and b's is 2, right? So this okay, so this if I that I talked about that thing, so that kind of relates to the value 2 here, right? And I mean, if you start with the prefix of length 0, that is epsilon, so that is 0. Okay, so that means here you have no difference between number of a's and b's. So when you reach here, covering the entire x, so there also there the difference is 2, right? So that means it has to pass through some point. It has to pass through some point where the difference is 1. Okay, so it has to reach this thing at some point, at some x1, right? At some prefix. So this is the argument that I made here, and this idea of thinking about this function and that it's going through all this intermediate values, so that's very helpful in solving other problems also. So for example, now instead of this thing in Hofcraft-Ullman, I think the problem is there, or you can find it elsewhere also. So it asks you to consider all this language. So you now take all this w's in again this a and b star, such that now the number of a's is twice that of number of b. Okay, so I instruct you to solve this and try to solve this yourself. Okay, just listening to worked out problems will not help. You have to solve the problems yourself. So try to solve this problem. I think this problem is also in Hofcraft-Ullman. So just try to solve this problem using that idea of that function that it must go through to some intermediate value. Okay, and you will see how this helps. So the idea is whenever you are trying to consider a production, you see that you have some string here, and that string either starts with A or it starts with B. So corresponding to that, you have two productions. So it either starts with A or it starts with B. It either starts with A or it starts with B. Now if it starts with A, what property should the remaining thing have? If it starts with B, what property should the remaining thing have? Okay, so the same thing you should apply for this problem, and then should come up with all the intermediate variables and what sort of properties should they have. So I can give you a hint that this thing will suffice. Again, it's you can do that using only this SAB, but now instead of having this thing, you have to consider sort of this difference, that number of so now you have to consider this difference, twice the number of B minus the number of A. You have to consider sort of this difference. So okay, so the next problem is similar. Now here we proved this for this thing, so both direction we have proved. Now this part is just same as this one, so this is just interchanging AB and this small a and small b, so this is exactly same as that we did for this part, so there is nothing more to prove. You see that the productions are symmetric with respect to A and B. So there is nothing more to prove for this part. It's just similar to this, and with all this proved, this whole thing is proved. So now the next problem is it looks quite similar. So in the earlier problem it was equal, right? Equal number of A's and equal number of B's. So here it says that all the strings where the number of A's is more than the number of B's. Okay. So again, without looking into the solution, you should first try to solve it yourself. Okay. So again, I think this is given as a problem in Hofstra-Pullman. So you should try to solve all those problems in the exercise. So here you see I'm using the same productions. Okay, so these three productions, it's same as what we used here, right? It's the same thing. Now on top of that, I'm using one more production here. And not only that, so for this I have this S prime, so and also I am starting from S prime, so this is now my start symbol, okay, instead of S. So I'm starting with S prime, and the rest are same. So now then what sort of strings are generated here? So you see again, I should break this up into two directions, so that if you derive something from S prime, then it should have this property, and if it has this property, then you should be able to derive it from here. So now if you can derive this thing, consider a leftmost derivation, okay, of this string. And what was the leftmost derivation? If you remember the definition, in a leftmost derivation, we always expand the leftmost variable. So we start with this thing, okay, and we can either have A or we can have this S prime A, and since it's a leftmost derivation, that means we have to expand this one. We cannot first expand this one. And as we said before that okay, if you have a derivation, you have a leftmost derivation. It doesn't mean that if you are only using leftmost derivation, then you won't be able to derive certain strings. So all that is important is that so here it means that you can derive this thing from here, so that means there is a leftmost derivation which you can use to derive this thing. So we are considering that leftmost derivation. We are not adding any extra constraint. So again, so in leftmost derivation it will be like this, and again this will be s prime a. So at some point of time you will have some bunch of a's and then this s prime, and finally this thing will change when you finally replace this s prime by some a using this part. So s prime goes to a, so finally you will have just a bunch of a's, right? So here if you just first use this a, then this k will be 1, right? So I'm not again using any special thing. So this is just I many steps where I get this a to the k. So but the point is, any leftmost derivation, the first thing that you get from s prime is some a to the k, right? And then from this a to the k you will have your final string, but that means that each of this k will be expanded into something. So this ith k in this k many a's, so that will be some wi, and all of these are derived from a, right? So each of them are derived from a. So now, since this part we have proved, we spent so much time to explain this part. So this means that here, if we are just consider, right? See, once you reach this point, so after that there is no s prime, right? So that means there is no. You are not going to use this production, so you are only using this productions. So then again, so by our previous problem, so we know that for each of this strings, the number of a's will be exactly 1 more than the number of b's, right? So if I take them together, that means in total the number of a's will be exactly k more than the number of b's, okay? Because there are k many such things, and for each of this thing there is 1 more a than b, right? So that means it has this property. So this implies this, and the other direction is just the same thing stated in reverse. So if this is greater than this, then that means this is this plus some k, some positive k, right? And by using this thing repeatedly, using something like this, I can first derive ak, and then from here I can derive this thing where each of this wi's are derived from a. So this means that if this is true, then I have such a derivation here. So in both ways, but this is where all the detail lie, right? So this is the part. So this includes all the proofs that we had before. So if you just try to prove this as a standalone problem, you have to go through all those things. But since we have done that, we can do this. But anyway, as I was saying, so now that you have these two similar looking problems, so you also try to solve this thing. So again, it looks almost same, but here the number of a's is twice that of the number of b's, okay?